this model here totally ignores the queuing capacity of the nodes, which basically means that, well, we all know you can fire 10 packets at a delay of 0 seconds, and they will actually return. But that doesn't mean that you can take 100 packets, and that will work as well. So the network has this limited queuing ability, and we will have to take care of that. And all of this suggests a new model, which is the bucket model, I called it.
If anyone knows who made the Cisco logo that was placed on the camp door, I'm going to buy him lots of beers.
Okay, so now we have a different objective. We don't want to find the optimal delay. We actually want to fill all the buckets. We want to make use of the complete queuing capacity. But we also have to make sure that we don't put too many packets in the buckets, because otherwise they will just drop. Okay, so yeah, that's basically the new question. And now if you look into, let's come back to the TCP congestion control. The funny thing is, these algorithms, which are used in TCP congestion control, actually pose this exact question. It's how many packets can be out there in the network at once, and not the question, what is the optimal delay between packet sends? And if you look into the Nmap code, you will see that Nmap actually makes use of TCP congestion control scheme. Well, it doesn't really implement it, but it makes use of those ideas. And that's the very classic TCP Reno, which dates back to, I think, the 80s, the early 80s. Okay. So the question is, of course, why don't we have this congestion control by default? I mean, if you're downloading something off a website, then of course you don't cause congestion collapses. So somehow that works. But that's just because you're doing that using TCP, and TCP does all of this under the hood for you. Now we are of course sending TCP packets, but in fact we're not dealing with an established TCP connection. They're basically just IP packets, and they happen to be TCP packets. The congestion control only starts after the connection has been established. So you'd be thinking, okay, well, we don't have this out of the box. Let's just take the algorithm and implement it. But that doesn't work, because the situation that TCP is in is quite different from the situation that port scanner is in. First of all, in TCP, the receiver actually acknowledges the packages. And if you think back to the filtered ports, this is not the case when you're port scanning. You may get an answer, the port is closed, the port is open, but also you may just not get an answer. And because of this, in TCP, timeouts are actually error conditions, while in port scanning, a timeout doesn't really mean anything. It just means that you didn't get a response quickly enough. And then something else, TCP has sequence numbers, and we don't really have sequence numbers, and we'll see why that is important. So in other words, the TCP receiver is cooperative, and the host, which is port scanned, is usually not very cooperative. Of course, that doesn't mean that we cannot force it to be cooperative, and that's basically the idea that we're using here. Triggers. Okay. So the idea is this. Before you start the actual port scan, try to find some packets which will generate responses. So for example, you send an ICMP echo request, you send TCP SYN on port 22, and you just see if you can get responses. Now if you do get a response, then this means that, oh wait a minute, no, wait, yeah. If you do get a response, no wait, Okay, and then you take these packets that will produce a response for sure, and then you insert them into your probe stream. So you send SYN to port 10, another one to 140, and then you insert your trigger packet, which is the one which will trigger a response, and you go on like that. So what's that good for? Well, the triggers now play the same role, the trigger responses now play the same role as the acknowledgements do in TCP. Because you can be absolutely sure that you should get a response, and if you don't get a response, well, that means that obviously the packet has been dropped. And that means that we get constant information about the network's actual performance. We know if packets were dropped, and we know it straight away. And now a timeout is actually a signal of error, similar to how it is in TCP. So let's take a look at what this means in practice. This is a plot of what an Nmap scan looks like if you're scanning a responsive host. And what you see on the y-axis is the number of packets which are out at once in the network, and you have the time on the x-axis. And of course, the host, by definition, nicely responds to us, so the timing works perfectly. You can see that in a few steps, Nmap kind of converges against the actual limit, the actual capacity of the network in use. Now, what Nmap forgot is what happens when you scan filtered hosts. That's the same plot. But we should be fair about this. I mean, what you see here, obviously, is that since there are no responses, it can't do any timing. So if you're scanning a filtered host, then basically it will just scan as slow as possible. But we should be fair about this. If an answer, let's just read the comment first. This is very nice in the Nmap source code. When a successful ping response comes back, it counts as this many normal responses because the fact that pings are necessary means that we aren't getting much input. So it basically means what they do is this describes a variable which tells us how much a response to a ping would count. And what they do is every 5 seconds in which they have not received an answer, so that's like an eternity, they send one ping probe. And if that returns, it counts as if 3 packets have returned correctly. Okay, so let's give you this in numbers. This is the difference between scanning a filtered host with Nmap on one side, all ports, 12 minutes and 18 seconds, and Port Bunny on the other side, 15 seconds. Okay, so I mentioned sequence numbers. What does this have to do with port scanning? Well, it turns out that sequence numbers can actually be used to detect packet drops early. Sequence numbers, basically you give each packet that you send a number, and this number will also be in the response. So what you can do is, if you've received a trigger response for 5, and then you receive a trigger response for 7, 8, and 9, then obviously trigger response 6 got lost. So you've detected a packet drop before the timeout clock was actually hit. And that's, in many cases, that really helps improve the responsiveness of your scanner. And if you take a look at how Nmap solves this problem without triggers, then you'll see that in this comment, a previous probe must have been lost, which means that Nmap can't detect a timeout, can't detect a drop packet before it has successfully resent that exact same packet and then received a response. because then it knows the packet it sent before must have dropped. So that's, that's not really responsive. And an important consequence of this is that Nmap has to resend the packets that could have dropped straight away. And this makes Nmap extremely vulnerable to a problem which we call the late responses problem, which you'll see right now. Because once the timeout clock has been hit, you have to decide to resend. Now the clock will not be very accurate, and there may just be some delays for some reason or another. And you start resending, because basically you have to know, did this drop or was this just a filtered port? And so you resend, and a little later you get a response for the initial probe. So you've just generated some extra traffic which you wouldn't have needed at all, and it's basically taking away some capacity that you could have used for probes that you actually want to send. And with triggers, you can actually defeat this problem, because you don't have to resend the exact same packet straight away. You can just send any other packet, because we're not doing the timing depending on the probes. We're doing the timing depending on the triggers. So now overall, what we've done is we've taken the problem of port scanning, and we've basically ported it to the TCP congestion control domain, because everything we expect of TCP is now also true for port scanning if you use triggers. So let's go through this. The receiver acts packets in TCP, and it also acknowledges triggers in port scanning. Timeouts are error conditions, and now with triggers, timeouts are also error conditions for port scanning. Sequence numbers are used. Yes, we're using sequence numbers too. We're integrating them into the triggers and are able to detect packet drops early now. So what are the benefits? Obviously, we can now scan filtered hosts, which we were not able to do before, really, because 13 minutes is just too much. Secondly, we can detect packet drops early, as just mentioned. And we don't have to immediately resend the probe which has just dropped or may have just dropped. Most of all, we've ported TCP into the congestion control domain, which means that we can implement other TCP congestion control algorithms, not just the one from 1980, but also new ones. And if you take a look at that development, you'll see that there are many different algorithms for different environments. You'll see algorithms for satellite systems and for wireless networks and all sorts of different environments. And we can make use of all of these algorithms. And that's something really new. Of course, there are also problems with triggers. Not all triggers have the same quality, because let's take an example. Let's use the ping trigger. Let's send ICMP echo requests. Then it may be so that there are ICMP rate limitations, while the probes are not rate limited at all. Then you'll scan a lot slower than you'd have to. TCP triggers are basically the best triggers because they, in most cases, behave just like the probes. This may be different if there's a quality of service, which basically means that you've defined that traffic on some particular port is going to be prioritized. Then, of course, probes may be too slow, or triggers are too slow. So the triggers are not really like the probes, and then that can be a problem. But it's usually not the case. And of course, a host may just not respond to any of our triggers, in which case we think it's down. Okay, how can you fix this? Well, you can at least do the following. You can try to use the best triggers always. which means first try the TCP SYN triggers because they're closest to the probes, then try the ICMP triggers, and last try the UDP triggers because destination unreachables are almost always